at Stockholm University. I work there with Jan Gudmundsson, who's also in this meeting, and who might interject at some point.
Yes.
So I want to talk a bit about, and I want to show actually how Beamconv works to convince you all that it's easy to use and easy to mess with. So the first thing I'm proposing is that I'm going to show you how to install Beamconv from scratch. And to do this, I have this terminal window that you can all see. And I'm just going to create a fresh conda environment with nothing on it. Okay, nothing in the hands, nothing in the sleeves. Just come.
So one thing that maybe can be used as a point for discussion while we're compiling and running code is there are some functionality in Beamconv that does not exist in other libraries that are being developed. And I'm sorry, so by the way, apologies for the background noise. My boys are downstairs getting ready for daycare. But one of the questions is whether should we actually try to port some of the functionality to libraries like Toast and LibRTSim, and if so, how should we do it? So that's a question that maybe we can have we can touch during this meeting. I'll give the word back to Alex.
Yes. So now that we're on a new shiny environment, it's liking a lot of things that astrophysicists like. So first, we're going to install NumPy. Hope you cannot hear my neighbors. Come on. Riveting content.
Will you be able to post all the the commands that you used just so that?
Sure. I mean, then we also need AstroPy. Not for Beamconv itself, but for one of the packages that Beamconv depends on, which is called QPoint, which handles the pointing through quaternions. I'll also add the links obviously to the Beamconv and QPoint repositories, since you cannot access them through conda, you have to clone into them. Right, and finally, the last dependence we have is MPI for Pine. Okay, now I already cloned into QPoint, which is C/Python library, C library with like Python wrapping. So it's going to be very simple to install it. Just from the install file. It should do all the compiling for me. Okay. Then I move to the Beamconv directory. Okay. There, we've installed Beamconv. Took us 6 minutes. I think there are some tests you can run too using PyTest. Is that right, Jan?
Yeah, but I guess you could just go directly to one of the notebooks too.
Yes. So if we look at what's in the Beamconv directory, we see there are a bunch of notebooks. And we are going to start where we should in the introduction notebook. So let me open that notebook. Huh. Yeah, I need to compile again with the 7. Not that part, sorry. I don't have the Jupyter matching my. I don't have Jupyter matching my my Python version, so I'll need to recompile Beamconv in the to reinstall Beamconv in the correct version.
Oops.
Yes, whoops.
So
But
actually, while you do that, should I jump in?
sure, if you want.
To answer Theodor Kisner's question on the chat, we haven't looked into that. I'm sure that would be a very good approach, especially now, given that difficulty finding. So Ted mentioned that there's a way to interface with both libconv and ducc. I don't know how to pronounce it, whether it's duck or something else within Toast. And I know that Martin Reinecke, who's responsible for duck, is chatting with Adi Dalvenorden, who's responsible for the core of the Beamconv code. And a lot of the functionality right now that have been developing for Beamconv is being pushed into, I think, duck. So I guess if that actually happens, then we'll be able to run some of the code that we've been developing from Toast. I don't know if Ted wants to comment on that, but that sounds like it's already.
Yeah, my comment was just that it's whatever, if there's a reasonable interface, we can certainly call multiple packages and pick whichever one we want for a given workflow.
Yeah. Great. So Alex, is it running now?
Yeah.
Oh, great.
I think it should be on everyone's screen.
Yes.
So Beamconv has several classes which are of interest to us: scan strategy, instrument, beam, tools, and in a further notebook we'll see the halfway plate class. The basic one is probably the beam. So a beam contains offsets and polarization, like offsets compared to the bore side, polarization angle, a name, a polarization type. It could be, you know, the A and B or B polarizer, a beam type, and if that's the case, you can have a full F maximum, maximum multiple, and then a number of other options. To create a beam, you just feed a beam object with the dictionary items you want. You can see that it's now we have a Gaussian beam with a full width half maximum of 40 arc minutes. An instrument is a collection of beams at a given position. You could have a telescope, or you could have it like a satellite or a telescope somewhere along the Earth with a few locations already pre-registered, like the South Pole and Atacama. A scan strategy, which you can either you can do constant elevation scan or fill or you can give it input quaternions. Marta will probably show you how she inputted a Lightbird-like scan strategy there. So let's make a telescope at the South Pole, scanning for an hour at 100 hertz. At 100 hertz, and add the beam we made earlier to the focal plane. We will input a constant elevation scans strategy centered in about that southern sky patch that we all love so much. That is probed by things like South Pole Telescope, or yeah, I think it's or is it the bicep patch? No,
I'm not sure. I think I probably put it in as the center of the bicep.
So it's okay. It's a bicep patch.
Yeah, it's been a while.
Yes, so you can define like how wide you scan through that patch, how fast you move in azimuth every second, how often you repoint to the center of the patch, the minimum elevation at which you scan, whether to cut values of the time stream that are smaller than the elevation. So we're just going to limit ourselves to like azimuthal throw and scan speed, and for the rest we'll trust the default positions. We load the WMAC power spectrum and make some spherical harmonic coefficients from it. So we want to decompose what Beamconv does. Now, at that point, you can probably just call scan instrument MPI here to perform the scan. We will see that in a further notebook, actually. Just a very bare bones way of getting maps from Beamconv. Let's break it down a bit. So the first thing that the scan strategy does is initialize the so-called detector pair. That create the spin maps, for which are the multiplications of the spherical harmonic coefficients of the beam and of the sky. Those spin maps are then evaluated at the given pointing coordinates by scan instrument MPI. Here we have a number of options so we don't interpolate our results. So we just have really what's at the given pixel at the given time. We saved the time order data, it's really more of a development and debug option, because it takes a lot of space. If we wanted to make maps, we would set binning to true. So we have one chunk can just plot the time order data for our Beamconv time stream. If we run with interpolation again, we get a much smoother signal. You can see again the first 50 samples of this 500 sample interval. You see that the interpolated version corrects for the whole the stepwise nature of the raw signal. Beamconv obviously is not limited just to Gaussian beams. After all, if we want to do beam convolution, it would be quite silly to stop to just one type of beam. So here we use an example beam that is from physical optics, which is elliptical Gaussian with a weak symmetry. So as you can see, the beam is no longer symmetrical. Its harmonic modes are quite a bit different. Right. And there are modes that are like azimuthally asymmetric. Think that all those m non-zero for the Gaussian beam will be 0. So here you can see that there are variations. But just like the other time, we can just scan with the beam. We tell our instrument now that it will rotate by 36 degrees every 100 seconds in addition to scanning constant elevation. We only scan on temperature. This way, any polarization we see is temperature to polarization leakage. So we do the scan for the Gaussian beam. We see that for a single pixel on the sky, that's on which we come back for different orientation angles. The signal is always the same. If we do it with the physical optics beam, let this turn a bit, yeah. We can see that the signal has changed, which means that we are experiencing temperature to polarization leakage. So this is, as you can see, it's fairly fast and fairly simple. I can do a third of a million of samples on my laptop with just one core in, well, I guess it was 15 seconds or so. Okay, so the second one I want to show you is just how to make maps with Beamconv. It's a more compact notebook. So, does anyone have any questions on the first one?
Yeah, I was going to ask, are there any questions? Maybe I can comment if there are no questions. That really the strength, I think, of this code is the fact that we're able to simulate beams that have Stokes IQ U and even Stokes V components, and we can scan Stokes IQ U and V realizations of the sky. And we have the ability to inject a bunch of optics-related non-idealities in a relatively simple manner. So that's the strength of the code. The code currently does not have functionality to the map making. So all the map making is based on viewpoint. It's naive binning. And we don't have things like 1RF noise or stuff like that, as part of the core functionality of the code. So that's some of the weaknesses at the moment. It's really focusing on optical non-idealities and running simulations without noise to understand how different aspects of our optics change the signal that we get in our time streams. Yeah.
Tony raised the hand.
Yeah,
I joined maybe a few minutes late, so I'm sorry if you touched on this right at the beginning, but there are a few tools on the market to deal with beam convolution, of course, going all the way back to things like PhoebeCop, then through libconvict, and now to Duke, however it's pronounced. Can you just sort of give me some idea what maybe what you just mentioned was one of them, but what the sort of advantages of the approach here is to some of those other tools?
Well, yeah. So I mean, so okay. So somebody should correct me if I'm wrong, but convict. Well, PhoebeCop is not great because it's a pixel domain convolution, and we know that the drawbacks that come with that. Convict is essentially using the same algorithm that Beamconv is using, right? It's a spherical harmonic domain convolution. The difference is that Beamconv actually is able to take as input Stokes IQ U and V realizations of the beam as opposed to just the Stokes I beam. And so it actually, it accounts for cross-polar leakage in a much more natural and correct way. And people that are actually working on pushing convicts, if somebody is on this call, should correct me. Duck lacks many of the functionalities that Beamconv has at the moment, but that is being improved on. Martin Reinecke, I don't know if he's actually on right now, but he and Adi Davenvoorten, who wrote Beamconv, are in frequent communication right now to actually push all the important functionality that is in Beamconv into Duck. So that I don't know, that maybe helps answering the question.
And of course Martin wrote convict also.
Yeah.
So it's all the same thing.
yeah, exactly. It's really, it's really just the fact that convict only has a Stokes I beam and not a Stokes Q, Stokes U, Stokes V beam. So that is one thing that is, clearly missing.
Yep.
And another thing that is clearly missing is just that, Beamconv is designed by people that actually work with instruments and work with optical, work with telescope designs. And so some of the options that we have as part of the code are sort of natural to expanding on sort of going from serial order approximation of a beam, which is a Gaussian, to an elliptical Gaussian, to a physical optics derived beam model, et cetera, et cetera.
Right.
Yeah.
So I don't have any great investment in PhoebeCop, but one of the advantages, or in some sense, one of the uses that it had was that it builds local approximations to the beam, which makes it easier in some sense to do things like point source deconvolution or searches. So different purpose maybe. So
it was great that you could get an effective beam as a functional location on the sky. Yeah, that was a really nice thing. But we can generate that with Beamconv as well, by scanning point sources at different locations.
Okay, that's useful.
Yeah.
Okay, so this one is about making maps. So again, we generate some LMs, Gaussian beams, set options for the spin map dictionaries. So the maximum spin mode we use is 2 because the beams are symmetrical. We put the end side. We set the end side of the scanned maps. Again, we define scan strategies, location, length of the mission. Now we create.
So Alex, just to know, so you have 5 more minutes, but we already had a discussion, so maybe you can use a few more minutes if you need.
Yes, I think. Right, this is going to take maybe a minute, so I launched that and I'll just excuse that. So really this is like the basic sequence you use. These 2 cells are the basic sequence you use every time you make a Beamconv. You want to make maps of Beamconv. You create a focal plane with some given beam options. So here we have we put Gaussian beams, but remember last time in the previous notebook, we showed how you could just input some file of physical optics beams. You decide how you're gonna split your data between your data between chunks, which is useful if you have multiple cores. You allocate space for the maps since you're interested in map making. You decide how your instrument will rotate. You decide the elevation steps for a constant elevation scan. You decide how the half-wave plate will be modulated. So it could be continuous, fixed, or stepped. You can even pass an argument that there is no, that could have no half-wave plate. Then you call scan instrument MPI with your scan options, which here are just the coordinates at which you're scanning and the azimuthal throw you have. And right, and then the time streams are in there, and the time streams, the positions are in there, and you call solve for map to get nice maps. So here is a map of the condition number, which is a quality factor for the various maps. So it's not, it shouldn't be microkelvin CMB, it's just it should just be adimensional. And then you send CDI, Q, and new map. And actually, if we smooth our input map, compare input at output, we see decent agreement up to 10 to the minus 10 microkelvin. So obviously there is some difference in the Q and U maps, but to vanishingly low level. Right. The final thing I wanted to show was the half-wave plate class, because this is one of the things we have implemented recently in Beamconv, right? So for the interest of time, I'm not going to run it, but basically the beam can have as attribute half-wave plate object, which is given by a half-wave plate class. There are a number of predefined half-wave plates already inside models already inside base Beamconv. So you can call the choose half-wave plate model of the half-wave plate to see a stack of isotropic and birefringent materials with different thicknesses, refractive indices, loss tangents, and angles, and maybe angles to the extraordinary axis. When it's provided with a half-wave plate, the beam will compute the Mueller matrix for that half-wave plate. You can see this traditional 4x4 form. Here we have, since we have like a one-layer Mueller matrix, it has 4 independent components, one that does the 2 first diagonal elements, 1 for the 2 last diagonal elements, and 2 for the cross element. You can also create your very own half-wave plate or your very own dielectric by calling the stack builder method and supplying it with arrays of the thicknesses, the indices, the losses, and the relative orientation angles. So here I made one with isotropic material that has a 1 refractive index no loss tangent, and then some dummy birefringent material. But what you really, but usually what you call is the set half-wave plate Mueller method. You create your beam, then you go to the set half-wave plate Mueller method, where you either give a model name or the thicknesses, refractive indices, loss tangent, and angles, orientation angles you're interested in, and it calculates it. Oh, right, because I didn't actually run the notebook before. Then if you have supplied any half-wave plate that is not any kind of half-wave plate to Beamconv, it will automatically know that it should scan. It should include the neural matrix of the non-ideal half-wave plate. If you don't supply half-wave plate, it will default to the ideal half-wave plate behavior. Right. I think I'll just zoom over this. So really, again, it's the same steps to create time ordered data. Here we have a bunch of different half-wave plate models, including one with several layers of birefringent material. This might take a few minutes. 3BR and 5BR refer to the number of birefringent layers in there, but again, you can use the example at the top to create your very own neural matrix for a half-wave plate. And you can scan how polarization gets modulated. Well, how a half-wave plate rotates, how it differs from an ideal half-wave plate model. And you can see, like, okay, I should have taken the square there, but you can see the half-wave plate modulation here.
So actually, you're running out of time now.
Yes. So I guess I'll just stop talking and ask if anyone has questions over this last part. Again, I'll put the links to the repository with the notebooks and how to install it at the end. Thank you.